like to welcome you to this course on computer science. Actually, that's a terrible way to start. Computer science is a terrible name for this business. First of all, it's not a science. It might be engineering, or it might be art. Or we'll actually see that computer, so-called science, actually has a lot in common with magic. And we'll see that in this course. So it's not a science. It's also not really very much about computers. And it's not about computers in the same sense that physics is not really about particle accelerators. And biology is not really about microscopes and petri dishes. And it's not about computers in the same sense that geometry is not really about using surveying instruments. In fact, there's a lot of commonality between computer science and geometry. Geometry, first of all, is another subject with a lousy name. The name comes from Gaia, meaning the earth, and metron, meaning to measure. Geometry originally meant measuring the earth or surveying. And the reason for that was that thousands of years ago, the Egyptian priesthood developed the rudiments of geometry in order to figure out how to restore the boundaries of fields that were destroyed in the annual flooding of the Nile. And to the Egyptians who did that, geometry really was the use of surveying instruments. Now, the reason that we think computer science is about computers is pretty much the same reason that the Egyptians thought geometry was about surveying instruments, and that is when some field is just getting started and you don't really understand it very well, it's very easy to confuse the essence of what you're doing with the tools that you use. And indeed, on some absolute scale of things, we probably know less about the essence of computer science than the ancient Egyptians really knew about geometry. Well, what do I mean by the essence of computer science? What do I mean by the essence of geometry? See, it's certainly true that these Egyptians went off and used surveying instruments, but when we look back on them after a couple of thousand years, we say, gee, what they were doing, the important stuff they were doing, was to begin to formalize notions about space and time, to start a way of talking about mathematical truths formally that led to the axiomatic method, that led to sort of all of modern mathematics. Figuring out a way to talk precisely about so-called declarative knowledge, what is true. Well, similarly, I think in the future, people will look back and say, yes, those primitives in the 20th century were fiddling around with these gadgets called computers. But really what they were doing is starting to learn how to formalize intuitions about process, how to do things. Right. Right. Starting to develop a way to talk precisely about how to knowledge, as opposed to geometry that talks about what is true. Let me give you an example of that. Let's take a look. Here is a piece of mathematics, right, that says what a square root is. Right? The square root of x is the number y, such that y squared is equal to x, and y is greater than 0. Now, that's a fine piece of mathematics, but just telling you what a square root is doesn't really say anything about how you might go out and find one. All right, so let's contrast that with a piece of imperative knowledge, right? How you might go out and find a square root. This, in fact, also comes from Egypt, not ancient Egypt. This is an algorithm due to Heron of Alexandria called How to Find a Square Root by Successive Averaging. And what it says is that in order to find a square root, you make a guess, you improve that guess, and the way you improve the guess is to average the guess and x over the guess, and we'll talk a little bit later about why that's a reasonable thing. And you keep improving the guess until it's good enough. Right? That's a method. That's how to do something, as opposed to declarative knowledge that says what you're looking for. Right? That's a process. Well, what's a process in general? It's kind of hard to say. You can think of it as like a magical spirit that sort of lives in the computer and does something. And the thing that directs a process is a pattern of rules called a procedure. So procedures are the spells, if you like, that control these magical spirits that are the processes. And, well, I guess, everyone needs a magical language. And sorcerers, right, real sorcerers use ancient Akkadian or Sumerian or Babylonian or whatever. We're going to conjure our spirits in a magical language called Lisp, which is a language designed for talking about, for casting the spells that are procedures to direct the processes. Now, it's very easy to learn Lisp. In fact, in a few minutes, I'm going to teach you essentially all of Lisp. I'm going to teach you essentially all of the rules. And you shouldn't find that, that particularly surprising. That's sort of like saying it's very easy to learn the rules of chess, and indeed in a few minutes you can tell somebody the rules of chess. But of course that's very different from saying you understand the implications of those rules and how to use those rules to become a masterful chess player. Well, Lisp is the same way. We're going to state the rules in a few minutes, and it'll be very easy to see, but what's really hard is going to be the implications of those rules, right? How you exploit those rules to be a master programmer. And the implications of those rules are going to take us the whole rest of this subject and, of course, way beyond. Okay, so in computer science, we're in the business of formalizing this sort of how-to imperative knowledge, right? How to do stuff. And the real issues of computer science are, of course, not, telling people how to do square roots, because if that was all it was, there would be no big deal. The real problems come when we try to build very, very large systems, right? Computer programs that are thousands of pages long, so long that nobody can really hold them in their heads all at once. And the only reason that that's possible is because there are techniques for controlling the complexity of these large systems. And these techniques for controlling complexity are what this course is really about. And in some sense, that's really what computer science is about. Now, that may seem like a very strange thing to say, because after all, a lot of people, besides computer scientists, deal with controlling complexity, right? A large airliner is an extremely complex system, and the aeronautical engineers who design that are dealing with immense complexity. But there's a difference between that kind of complexity and what we deal with in computer science. And that is that computer science, in some sense, isn't real. You see, when an engineer is designing a physical system that's made out of real parts, right, the engineers who worry about that have to address problems of tolerance and approximation and noise in the system. So, for example, as an electrical engineer, I can go off and easily build a one-stage amplifier or a two-stage amplifier, and I can imagine cascading a lot of them to build a million-stage amplifier, but it's ridiculous to build such a thing, because long before the millionth stage, the thermal noise in those components way at the beginning is going to get amplified and make the whole thing meaningless. Computer science deals with idealized components. Right? We know as much as we want about these little program and data pieces that we're fitting things together. Right? So we don't have to worry about tolerance, and that means that in building a large program, there's not all that much difference between what I can build and what I can imagine. Because the parts are these abstract entities that I know as much as I want. I know about them as precisely as I'd like. So as opposed to other kinds of engineering where the constraints on what you can build are the constraints of physical systems, the constraints of physics and noise and approximation, the constraints imposed in building large software systems are the limitations of our own minds. So in that sense, computer science is like an abstract form of engineering. It's the kind of engineering where you ignore the constraints that are imposed by reality. Okay, well, what are some of these techniques? They're not special to computer science. First technique, which is used in all of engineering, is a kind of abstraction called black box abstraction. Right? Take something and build a box about it. Let's see, for example, we looked at that square root method. I might want to take that and build a box. It sort of says to find the square root of x, and that might be a whole complicated set of rules, and that might end up being a kind of thing where I can put in, say, 36 and say, what's the square root of 36? And out comes 6. Right? And the important thing is that I'd like to design that so that if George comes along and would like to compute, say, the square root of a plus the square root of b, he can take this thing and use it as a module without having to look inside and build something that looks like this. It might be an a and a b and a square root box and another square root box and then something that adds. That would put out the answer. And you can see, just from the fact that I want to do that, is from George's point of view, the internals of what's in here should not be important. So for instance, it shouldn't matter that when I wrote this, I said, I want to find the square root of x. I could have said the square root of y, or the square root of a, or anything at all. Right? That's the fundamental notion of putting something in a box, using black box abstraction to suppress detail. And the reason for that is you want to go off and build bigger boxes. Now, there's another reason for doing black box abstraction other than you want to suppress detail for building bigger boxes. Sometimes you want to say that your way of doing something, your how-to method, is an instance of a more general thing. And you'd like your language to be able to express that generality. Let me show you another example, sticking with square root. Let's go back and take another look at that slide with the square root algorithm on it. Right, remember what that says. That says in order to do something, I make a guess, and I improve that guess, and I sort of keep improving that guess. Right, and so there's the general strategy of I'm looking for something, and the way I find it is that I keep improving it. Now that's a particular case of another kind of strategy for finding a fixed point of something. See, a fixed point of a function, a fixed point of a function is a value, fixed point of a function f is a value y such that f of y equals y. And the way I might do that is start with a guess, and then if I want something that doesn't change when I keep applying f, I'll keep applying f over and over until that result doesn't change very much. Right, so there's a general strategy. And then, for example, to compute the square root of x, I can try and find a fixed point of the function which takes y to the average of x over y. And the idea of that is that if I really had y equal to the square root of x, then y and x over y would be the same value. They'd both be the square root of x, right? Because x over the square root of x is the square root of x. And so the average, if y were equal to the square root of x, then the average wouldn't change. Right? So the square root of x is a fixed point of that particular function. Now what I'd like to have, I'd like to express the general strategy for finding fixed points. So what I might imagine doing is to be able to use my language to define a box that says fixed point. Just like I could make a box that says square root, and I'd like to be able to express this in my language. Right? So I'd like to express not only the imperative how-to knowledge of a particular thing like square root, but I'd like to be able to express the imperative knowledge of how to do a general thing like how to find fixed point. And in fact, let's go back and look at that slide again. See, not only is this a piece of imperative knowledge, how to find a fixed point, but over here on the bottom there's another piece of imperative knowledge which says one way to compute square root is to apply this general fixed point method. So I'd like to also be able to express that imperative knowledge. What would that look like? That would say this fixed point box is such that if I input to it the function that takes y to the average of y and x over y, then what should come out of that fixed point box is a method for finding square roots. So in these boxes we're building, we're not only building boxes that you input numbers and output numbers, we're going to be building in boxes that, in effect, compute methods like finding square root. And my take is their inputs functions, like y goes to the average of y and x over y. Right? The reason we want to do that, see, the reason this is a procedure, will end up being a procedure, as we'll see, whose value is another procedure. The reason we want to do that is because procedures are going to be our ways of talking about imperative knowledge. And the way to make that very powerful is to be able to talk about other kinds of knowledge. So here is a procedure that, in effect, talks about another procedure. Right? A general strategy that itself talks about general strategies. Okay, well, our first topic in this course, there'll be three major topics, will be black box abstraction. Let's look at that in a little bit more detail. What we're going to do is we'll start out talking about how Lisp is built up out of primitive objects. Right? What does the language supply with us? And we'll see that there are primitive procedures and primitive data. Then we're going to see how do you take those primitives and combine them to make more complicated things. Right? Means of combination. And what we'll see is that there are ways of putting things together, putting primitive procedures together to make more complicated procedures. And we'll see how to put primitive data together to make compound data. Then we'll say, well, having made those compound things, how do you abstract them? How do you put those black boxes around them so you can use them as components in more complex things? And we'll see that's done by defining procedures and a technique for dealing with compound data called data abstraction. And then what's maybe the most important thing is going from just the rules to how does an expert work? How do you express common patterns of doing things, like saying, well, there's a general method of fixed point and square root is a particular case of that. And we're going to use, I've already hinted at it, something called higher order procedures, namely procedures whose inputs and outputs are themselves procedures. And then we'll also see something very interesting. We'll see as we go further and further on and become more abstract, there'll be the line between what we consider to be data and what we consider to be procedures is going to blur at an incredible rate. Okay. All right, well, that's our first subject, black box abstraction. Let's look at the second topic. I can introduce it let's use it like this. See, suppose I want to express the idea. Remember, we're talking about ideas. Suppose I want to express the idea that I can take something and multiply it by the sum of two other things. So, for example, I might say, if I add 1 and 3 and multiply that by 2, I get 8. But I'm talking about the general idea of what's called linear combination, that you can add two things and multiply them by something else. It's very easy when I think about it for numbers, but suppose I also want to use that same idea to think about, I could add two vectors, a1 and a2, and then scale them by some factor x and get another vector. Or I might say I want to think about a1 and a2 as being polynomials, and I might want to add those two polynomials and then multiply them by 2 to get a more complicated one. Or a1 and a2 might be electrical signals, and I might want to think about summing those two electrical signals and then putting the whole thing through an amplifier, multiplying it by some factor of 2 or something. The idea is I want to think about the general notion of that. Now, if our language is going to be a good language for expressing those kind of general ideas, if I really, really can do that, so I'd like to be able to say, I'm going to multiply by x the sum of a1 and a2, and I'd like that to express the general idea of all different kinds of things that a1 and a2 could be. Now, if you think about that, there's a problem, because after all, the actual primitive operations that go on in the machine are obviously going to be different if I'm adding two numbers than if I'm adding two polynomials, or if I'm adding the representation of two electrical signals or waveforms. Somewhere there has to be the knowledge of the kinds of various things that you can add and the ways of adding them. Now, to construct such a system, the question is, where do I put that knowledge? How do I think about the different kinds of choices I have? And if tomorrow George comes up with a new kind of object that might be added and multiplied, how do I add George's new object to this system without screwing up everything that was already there? All right, well, that's going to be the second big topic, the way of controlling that kind of complexity. And the way you do that is by establishing conventional interfaces. Agreed upon ways of plugging things together. Just like in electrical engineering, people have standard impedances for connectors. And then you know if you build something with one of those standard impedances, you can plug it together with something else. Right, so that's going to be our second large topic, conventional interfaces. What we're going to see is first we're going to talk about the problem of generic operations, which is the one I alluded to, things like plus that have to work with all different kinds of data. So we talk about generic operations. Then we're going to talk about really large-scale structures. How do you put together very large programs that model the kinds of complex systems in the real world that you'd like to model? And what we're going to see is that there are two very important metaphors for putting together such systems. One is called object-oriented programming, where you sort of think of your system as a kind of society full of little things that interact by sending information between them. And then the second one is operations on aggregates, called streams, where you think of a large system put together kind of like a signal processing engineer puts together a large electrical system. That's going to be our second topic. Now, the third thing we're going to come to, the third basic technique for controlling complexity is making new languages. Because sometimes when you're sort of overwhelmed by the complexity of a design, the way that you control that complexity is to pick a new design language. And the purpose of the new design language will be to highlight different aspects of the system. It'll suppress some kinds of details and emphasize other kinds of details. this is going to be the sort of the most magical part of the course. We're going to start out by actually looking at the technology for building new computer languages, and the first thing we're going to do is actually build in Lisp. We're going to express in Lisp the process of interpreting Lisp itself, and that's going to be a very sort of self-circular thing. There's a little mystical symbol that has to do with that. We'll see the process of interpreting Lisp is sort of a giant wheel of two processes, apply and eval, which sort of constantly reduce expressions to each other. And then we're going to see all sorts of other magical things. Here's another magical symbol. This is sort of the Y operator, which is, in some sense, the expression of infinity inside our procedural language. We'll take a look at that. In any case, this section of the course is called metalinguistic abstraction. Abstracting by talking about how you construct new languages. As I said, we're going to start out by looking at the process of interpretation. We're going to look at this apply-eval loop and build Lisp. Then, just to show you that this is very general, we're going to use exactly the same technology to build a very different kind of language, a so-called logic programming language, where you don't really talk about procedures at all that have inputs and outputs. What you do is talk about relations between things. And then finally, we're going to talk about how you implement these things very concretely on the very simplest kind of machines. Even we'll see something like this, this is a picture of a chip, which is the Lisp interpreter that we will be talking about, done in hardware. Okay. Well, there's an outline of the course, 3 big topics: black box abstraction, conventional interfaces, metalinguistic abstraction. Now let's take a break now, and then we'll get started.